Hello everyone, and welcome to Applied Optimization Problem. So the goal of this section is to compute global maximum and global minimums of continuous functions over an interval where the function models an applied problem. So typically coming from a word problem. So the difference between pure and applied optimization problem is that in the pure setting, we already have a function and we already have an interval, and the goal is to find the global maximum and the global minimum of that function over that interval. For applied optimization problem, typically you need to find either the global maximum or the global minimum of a function, but the function is not given to you, and also the interval of optimization is not given to you. The thing that is given to you is a fat paragraph, and the first thing you need to do is construct that function that you need to maximize or minimize, and you need to figure out what is the interval for that optimization problem. So you need to go from that paragraph and then transform it into a pure problem. And in this section with my videos, I will give you a bunch of examples of how to transform a word problem, an applied optimization problem, to a pure optimization problem. To go from the applied problem to the pure problem, I'm going to give you a bunch of guidelines to help you along the way. So, optimization coming from word problems. The first thing you need to do, of course, is read the question carefully. A lot of you start and you just look for keywords and then you write down an equation and you start to differentiate or compute some limits or just do some BS computation. You have to be careful. Make sure you read the question carefully so that you can identify the quantity to optimize. Typically in an applied setup, we're not looking for both global minimum and global maximum. We're looking for one of them. Like, oh, let's minimize the time. Let's maximize profit. So it's one or the other. But it's still going to follow the pure ideas, because if you know how to find the global min and global max, well, you know how to find one of them. Once you have a clear picture of which quantity you need to minimize or maximize, then make sure you identify and label all the variables that you need in order to optimize that quantity. And then write the equation of that quantity to optimize as a function of all those variables. But of course, initially, even if you need a lot of variables, this is a course where the optimization problem needs to be a function of one variable only. So typically the word problem will have a lot of information in order to get rid of most of the variables except one. And to do that, you need to find all the constraint equations. Those equations are for any fixed or linked quantities by the problem. So typically we say, suppose we have an area that is equal to this, or there's always some sort of fixed quantity, or we have some sort of a relationship between those variables, like a geometric constraint or something that will allow us to substitute that information back in so that our equation becomes a function of one variable. So it's very, very key here. You need to make sure that the quantity to maximize or minimize is a function of one variable before you start to do any calculus stuff. So then you have to use all those constraints in that step in order to rewrite that equation so that your function depends on one variable. And then once you have that equation that depends on only one variable, you need to find the interval of optimization. So like in these questions, like the variables that you define in order to maximize or minimize your quantity will have some minimum maximum value, and this will be your domain for your pure optimization problem. And once you have your pure optimization problem, then you just optimize your function over your interval. So this is really the 6.4 part. And today what I'm going to do is I'm going to present to you examples of word problem until I make it down to a pure problem. So I'm going to translate from big fat paragraph to a nice function with one simple interval. All right, let's look at some examples. Bob has a goat named Goatron Prime. Bob's mom has 100 meters of fences. She wants to build 2 rooms for them to play, one circular room and one square room. Find the perimeters of the 2 rooms that minimize the total area of the rooms. So here we want to minimize the total area of the 2 rooms. So from the word problem, this is the quantity to minimize. So it needs to be clear which quantity do you need to maximize or minimize. In this question, we want to minimize the total area. So here we go. Boom. We want to minimize the total area of the 2 rooms. Let's call this total area by the letter big A. So we want to minimize the total area of the 2 rooms. So we need to understand clearly how these 2 rooms are constructed. So here, what are we starting with? We are starting with 100 meters of fences. So here we go, poof. And we need to cut that 100 meters of fences into 2 pieces. So the first piece, let's say we are using X meters of fences to construct the first room for the circular room. So that's called X, poof, the first chunk of that 100 meters of fences, and we're going to use that first X meters of fences to construct the circular room. So here we go. We are going to use poof, the first X meters for the circular room. So what does it look like? So here we go. So we're taking the first X meters and we're making the circular room. This is where Goatron Prime will live. So here we go. Poof. So I'm using X meters and I'm making this circular room. Circular. My God, I have a hard time saying that one. Because the first room is a circle, in a circle, the most important quantity to compute stuff with a circle, either the perimeter or the area, is the radius. I'm going to call R the radius of that round room. So this means that the circumference of that room is the same thing as X. So if you call the circumference, let's say C, we know C is the same thing as X. So we're using X meters to build the round room. So the circumference of that circle is, of course, X. And of course, the formula for the circumference of a circle is 2 pi r. So that's it for the round room. So this means that we're going to use the rest of the 100 meters. So if we're using X meters for the round room, we're going to use the rest, which is 100 minus X, to build the square room. Poof. So 100 minus X is the piece that we're going to use in order to construct the square room. So here we go. So poof. So we will use the other 100 minus X meters for the square room. All right, so let's look at it visually. So this is for the square room. We're using 100 minus X meters. So here we go. Poof. This will be the room for Bob. Aw, Bob looks so sad. So we're taking that 100 minus X meters of fence and we're just bending it into a square room. And as soon as you're dealing with a square in geometry, you should label one of the side and call it C. So really, really important because you can use that C to compute either the perimeter of that circle or the area of that circle. Because we're using 100 minus X meters to build the square room, this means that the perimeter of that room is 100 minus X. And then if you want to rewrite this perimeter as a function of C, then of course the formula for the perimeter of a square is simply 4 times C. So right now we have a lot of variables. We have X, the perimeter of the square rooms. We have R, the radius of that square, and we have like C, the side of the square room, and we know the perimeter of that square room is 100 minus X. And the goal is to construct a formula that will compute the area of those rooms. So we need to decide which variable should be used in order to compute a formula for the total area. In this question, the best variable is actually X. So we're going to find two equations, one equation for the radius as a function of X using the first equation of the perimeter that we know a relationship between X and R. And then we're going to construct also an equation for C as a function of X because we have another equation that links X and C together. Those are the two constraint equations. So even if initially there's three variables, there's no three variables. The only variable here is X, how much meters of fences you're using for the first room, and then the rest is for the second room. And the radius is not a choice, it's something you can compute as a function of X. Same thing for C, you can compute C as a function of X. In the first equation, let's isolate the radius as a function of X. So here, if you simply divide by 2 pi, you can see that X divided by 2 pi is R. So we have an equation that will allow us to replace the radius as a function of X. Let's do the same thing with the circle. So let's isolate C as a function of X. So here, if you want a formula for C, the only thing you have to do is divide by 4. So if you divide by 4 on both sides, you're going to get 100 divided by 4, which is 25. So here we get 25 minus X divided by 4, and this will be your equation for C. Remember, the goal is to minimize the total area. So let's construct a formula for the area of the circle, and also let's find a formula for the area of the square, and then we're just going to add those two together. So let's start with the circle. So let's call A round the area, of course, of the circle. That's initially pi r squared, but we want to rewrite everything with respect to X. So A circle is the same thing as pi. Open a big bracket and replace R by its freshly computed formula, X over 2 pi squared. And then if you square everything, you get that the area of the circle is pi X squared. So, and then over 2 pi squared, which is 4 pi squared. And you can simplify this a little bit by canceling the 2 pi's, canceling the 2 pi's, and you just get X squared over 4 pi. So we have a formula for the area of the circle as a function of X. Let's do the same thing for the area of the square room. So the area, let's call the area of the square room A squared. So squared, okay, so it's initially simply C squared, but we want something that depends on only one variable. So we now know that C is the same thing as 25 minus X over 4 squared. Now, if you FOIL this a little bit, you get that the area of the square is 25 squared, which is 625, plus 25 times minus X over 4 times 2. That will simplify to minus 25X over 2, plus the last term squared. So X over 4 squared will be X squared over 16. So now we have two formulas. One for the area of the circle, and it only depends on X. Nice. And we have another formula that will compute the area of the square room that will also only depend on X. And now we just need to add those two together. So now let's construct that final formula. So poof, the total area, which I call big A here, is just the area of the circular room plus the area of the square room. And when you do that, what do you get? So just combining those two formulas together, we get poof. So we have a area formula that only depends on X. And look at the notation here. If you As soon as you have a quantity that depends on only one variable, you can put that x in a bracket. So here we really are building a function for that total area that only depends on x. So it's going to be x squared over 4 pi plus 625 minus 25x over 2 plus x squared over 16. As soon as you have your function to maximize or minimize, in this case, we want to minimize the total area, you need to specify the interval. So our problem is almost pure. We have a formula that only depends on x. But here, what is the range of x? Well, x will be a number in between 0 and 100. Poof. So that's my interval. You could here include or not the endpoints. Both would be accepted. I will simplify the question here by including them. So if you include them, this basically tells us that you would allow the scenario where if x is 0, there's only one square room. If x is 100, there's only one circular room. So if you absolutely want two different rooms, you would say that x is strictly between 0 and 100. But in both cases, if you use an interval that includes the endpoint or not, you're going to reach the same final conclusion. And now this is the pure problem. So here I'm going to highlight the pure problem. Now we're back to a 6.4 type problem. We have a function that we want to minimize in this case over a closed interval. So now we're back to 6.4. We have a pure problem. Now that we're back to a pure problem, I'm just going to go over the computations very quickly, but make sure you know how to do this on your own. So if the question was a pure problem, like here's AX, let's find the global minimum over that interval. The first thing you always do is you find critical points inside the interval 0 to 100. So if you do that, first, of course, you compute the derivative of a, so a prime, you're going to get x over 2 pi minus 25 over 2 plus x over 8. This equation is always defined, so if there's any critical point, you will find them by setting them equal to 0. So here I'm just bringing the minus 25 over 2 on the right side, factoring x. I'll let you work with the algebra. But when you isolate x in this question, you will find that x needs to be 43.99 meters. And then, of course, that critical point is indeed inside the interval. The way you get to the final number, it does not need to actually follow exactly my steps here. As long as you compute a prime, you set it equal to 0, and you figure out a way to get that 43.99. And now, to reach our conclusion, we just need to build a table of output at the beginning of the interval, at the end of the interval, and at that critical point in between. When x is 0, the total area is 625. When x is 43.99, the total area is 350.06. And then when x is 100, the total area is 795.77. So this means that the maximum, the global maximum is when x is 100, and the global minimum is when x is 43.99. Because this question only asks to find the global minimum, the final answer, of course, is going to be the critical point. And this is very typical with these questions, that in applied word problem, that the critical point will be the answer. But in order to have a complete solution, you need to justify why that critical point is a global minimum. So here, the table of outputs of that function at the beginning, at the end, and at the critical point is the correct justification. So this means in order to minimize the total area, you will need to use 43.99 meters to build the circular room, and then you're going to use the rest, which would be 100 minus 43.99, which is 56.01 meters, to build the square room. All right, for that example and that video, that's it. That's all. Bye-bye.